chemical reaction is a process in which one or more substances is changed into one or more new substances. In this example, we have the reaction between hydrogen and oxygen gas to form liquid water. The reactants are always located on the left-hand side of the reaction, and the products are always located on the right-hand side of the reaction. The reactants and products are connected with an arrow, which points in the direction from reactants to products. Now, it's important to remember that chemical reactions must always be balanced. In other words, the same number and type of each atom must appear on both sides of the reaction. The reactants are located on the left-hand side, and the products are located on the right-hand side. In this case, we have 2 times 2 equals 4 hydrogens on the left-hand side and 4 hydrogens on the right-hand side. We also have 2 oxygens on the left-hand side, and we have 2 oxygens on the right-hand side. Therefore, this reaction is balanced. An important skill in chemistry is being able to interpret chemical reactions. In this example, where we have hydrogen plus oxygen reacting to form water, we can interpret this as 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of liquid water, or we can interpret this as 2 molecules of hydrogen, as we see here, react with 1 molecule of oxygen to form 2 molecules of water. Both of these interpretations are valid. However, it's important to remember that it does not mean that 2 grams of hydrogen react with 1 gram of oxygen to form 1 gram of water. It only works for moles and molecules. One of the most fundamental skills in chemistry is the ability to balance chemical reactions. It's important to remember that an equation can only be balanced by adjusting the coefficients of the formulas. So, for example, in this unbalanced reaction, NO plus O2 produces NO2, we cannot introduce extraneous atoms. So, for example, we cannot introduce the oxygen atom as shown here. Also, it's important that we can never change a formula just to balance a reaction. So we cannot change NO2 to NO3 in order to balance it. What can we do? We can adjust the stoichiometric coefficients in front of each of the compounds. So for example, you see here that there's 1 nitrogen on the left and 1 nitrogen on the right. The nitrogens are obviously balanced. However, if we look at the oxygens, we have 1 plus 2, 3 oxygens on the left and 2 oxygens on the right. So what we could do is add the stoichiometric coefficient 1/2 in front of this oxygen. This would give us 1 plus 1/2 times 2 equals another 1, or 2 oxygens on the left-hand side, and we have 2 oxygens on the right-hand side. Since the nitrogen and oxygens are balanced, this reaction is balanced. However, in chemistry, we usually like to use whole numbers instead of fractions. So if we multiply this reaction by 2, we come to this reaction, giving us 2NO plus O2 produces 2NO2. And this is the form of the balanced chemical reaction that is most often seen in chemistry, although the other one here is also valid. Balancing chemical reactions is an important fundamental skill that you will be responsible for in the course. The first step to balancing a reaction is to write the correct formula for each of the reactants and products. So in this example, we have ethane reacting with oxygen to form carbon dioxide and water. The chemical formulas for each of these are C2H6 for ethane, oxygen is a bimolecular gas, carbon dioxide is CO2, and water is H2O. Putting these together gives us C6H6 plus O2 produces CO2 plus H2O. Now this is the unbalanced reaction. In order to balance a reaction, what we have to do is adjust the coefficients in front of each of the formulas so that the number of atoms on the left-hand side, the reactant side, and the right-hand side, the product side, are balanced. However, we are not allowed to change the subscripts in the compounds. So for example, we can write 2CO2, but we cannot write C2O4 because this would completely change the chemical nature of carbon dioxide. The next step is to start by balancing the elements that appear in only one reactant and one product. So in the example we have here, we can see that we would want to start by balancing either carbon or hydrogen, but not oxygen, because carbon only appears in one compound in the reactants and one compound in the products. And hydrogen also only appears in one compound in the reactants and one compound in the product. However, oxygen, while it only appears in one compound in the reactant, appears in two compounds in the products. So we want to balance the oxygens last. So starting with carbon, we see that we have two carbons on the left-hand side, but we only have one carbon on the right-hand side. So in order to balance the carbons, we would want to multiply CO2 by 2, which would give us C2H6 plus O2 produces 2CO2 plus H2O. Now, looking at the hydrogens, we see that we have 6 hydrogens on the left and 2 hydrogens on the right. So in order to balance the hydrogens, we would want to multiply water by 3, which would give us 2CO2 plus 3 H2O on the product side, or the right-hand side. Finally, we want to balance the elements that appear in 2 or more reactants or products. And in this case, that element would be oxygen. You can see that we have 2 oxygens on the left, and we have 2 times 2 is 4 oxygens over here in CO2, and 3 times 1, so that's another 3 oxygens from water, giving us 4 plus 3 equals 7 oxygens on the right-hand side. So in order to get 7 oxygens on the left-hand side, we would multiply oxygen, O2, by 7 halves, leaving us with this as our balanced chemical reaction. Now, the reaction as it's written here is perfectly balanced. However, in chemistry, usually we don't like to have fractions in our balanced reactions. So what we would do to remove the fraction is multiply everything in the reaction by 2. And this would give us 2C2H6 plus 7O2 produces 4CO2 plus 6H2O. And that is the balanced chemical reaction. Now the last step is to check that both the number and type of the atoms on both sides of the reaction are the same. So looking at our balanced chemical reaction, on the left-hand side we have 2 times 2 equals 4 carbons, and we have 4 carbons on the right-hand side. Looking at the hydrogens, we have 2 times 6 hydrogens equals 12 hydrogens on the left-hand side, and on the right-hand side we have 6 times 2 equals 12 hydrogens on the right-hand side. Finally, if we look at the oxygens, we have 7 times 2 is 14 oxygens on the left-hand side, and we have 2 times 4 plus 6 oxygens, giving us 14 oxygens on the right-hand side. So we can see that on the left-hand side in the reactants, we have 4 carbons, 12 hydrogens, and 14 oxygens. And on the product side, or the right-hand side, we have 4 carbons, 12 hydrogens, 14 oxygens. So our reaction is balanced. So to summarize, the strategy for balancing chemical reactions is number 1, to balance the elements that occur only in one compound on each side first. 2, to balance free elements last. And 3, fractions and the coefficients can be cleared at the end by multiplying. In this example, we're asked to balance a reaction resulting from the complete combustion of a carbohydrate, C6H14O4. You'll notice that for complete combustion of carbohydrates and hydrocarbons, CO2 and H2O are always produced as the products. The first step to balancing the reaction is to look at elements only present in one compound in the reactant and one compound in the product. And the first element we'll look at is carbon, because it's only present in a carbohydrate on the left and only present in CO2 on the right. On the left we have 6 carbons, on the right we only have 1 carbon. So in order to balance the carbons, we'll place a 6 in front of the CO2, giving us 6 carbons on the left and 6 carbons on the right. Next we'll look at hydrogen, because again it is only present in one compound on the left, our carbohydrate, and only present in water on the right. We have 14 hydrogens on the left, and we have 2 hydrogens on the right. So in order to balance the hydrogens, we put a 7 in front of the waters, giving us 14 hydrogens on the left and 14 hydrogens on the right. Lastly, we'll balance the oxygen because it is present in all the reactants and all the products. On the left-hand side, we have 4 plus 2, which is 6 oxygens. On the right, we have 6 times 2 is 12 oxygens plus another 7 oxygens, giving us 19 oxygens. So in order to balance the oxygens, we'll take the 19, subtract the 4 oxygens from the carbohydrate. That leaves us 15 oxygens. And we'll take the 15 and divide it by 2, giving us 15 over 2, O2. Now, as it stands, this reaction is completely balanced. However, in chemistry, we usually don't like to have fractions in our balanced reactions. So in order to eliminate the fraction, we'll multiply the whole reaction by 2. This gives us 2C6H14O4 plus 15O2 plus 12CO2 plus 14H2O. Last step here is to check that the reaction is balanced. So here we have 2 times 6 is 12 carbons on the left. We have 12 carbons on the right. We have 2 times 14 is 28 hydrogens on the left, and we have 14 times 2 is 28 hydrogens on the right. Lastly, we'll take a look at the oxygens. We have 2 times 4, which is 8 oxygens, plus 15 times 2, which is 38 oxygens on the left. And we have 12 times 2 is 24 oxygens on the right, plus 14 oxygens, giving us 34 oxygens on the right, and the reaction is balanced. Here we're asked to write the balanced chemical reaction resulting from the decomposition of solid ammonium nitrate, which produces dinitrogen monoxide and water vapor. Now, here we're given both the reactant and the products. However, in order to solve the problem, we're going to need the chemical formulas of these. So you might remember that ammonium has the formula NH4+, and nitrate has the chemical formula NO3-. Putting these together gives us the chemical formula for ammonium nitrate, which is NH4NO3. Dinitrogen monoxide has the chemical formula N2O, and water has, you should know, has the chemical formula H2O. So putting these together gives us the unbalanced reaction. So we start with the ammonium nitrate, which we know decomposes to N2O and H2O. So in order to balance reaction, let's look at the elements here. Starting with nitrogen, we'll notice we have 2 nitrogens on the left and 2 nitrogens on the right. Next, we'll take a look at hydrogen. We have 4 hydrogens on the left and only 2 hydrogens on the right. So in order to balance the hydrogens, we would add a 2 in front of the water. Lastly, we'll look at the oxygens. We have 3 oxygens on the left, and 1 plus 2 gives us 3 oxygens on the right. So this reaction is balanced. Rocket boosters of the space shuttle use a fuel mixture primarily composed of ammonium perchlorate and aluminum. Given the unbalanced chemical reaction shown here, we are asked to calculate the minimum mass of ammonium perchlorate that is required to react with 1 kilogram of aluminum. So the strategy here is first to write the balanced chemical reaction. And we'll do this first before we continue with the rest of the question. Looking at ammonium perchlorate, you notice we have 1 chlorine on the left, and we have 3 chlorines on the right in aluminum chloride. So in order to balance the chlorines, we add a 3 in front of the ammonium perchlorate. Next, we'll balance the hydrogens. You'll notice that there are 3 times 4, giving us 12 hydrogens on the left, and we only have 2 hydrogens on the right. So to balance the hydrogens, we'll take 12 and divide by 2, giving us 6 waters. Next, we'll balance the nitrogens. We have 3 nitrogens on the left and 2 nitrogens on the right. So we'll take 3 divided by 2, gives us 3 halves and 2. Nitrogens are now balanced. Next, we'll try and balance the oxygens. You'll notice that on the left we have 3 times 4, giving us 12 oxygens, whereas on the right we have 3 plus 6, 9 oxygens. So this part of the reaction is already balanced, so we'll try to balance the oxygens using the aluminum oxide. So 12 oxygens minus 6 oxygens is 6 oxygens, and 6 divided by 3 gives us 2. So we have put a 2 in front of the aluminum oxide. The oxygens are now balanced. Lastly, we will balance the aluminums. We have 2 times 2 giving us 4 plus 1 is 5 aluminums on the right. So in order to balance the aluminums on the left, we would put a 5 in front of the aluminum. This reaction is now balanced. Now, we can address the rest of the question, which is to calculate the mass of ammonium perchlorate required to react with 1 kilogram of aluminum. So starting with 1 kilogram of aluminum, we want to calculate the mass of ammonium perchlorate. So in order to do that, we would convert our 1 kilogram of aluminum to moles of aluminum. Then we would calculate the moles of ammonium perchlorate, and then use that to calculate the mass of ammonium perchlorate. So the strategy here to get the mass of ammonium perchlorate, we need the moles of ammonium perchlorate. To get that, we need the moles of aluminum, and we need the mass of aluminum, which is given. Now, since we have a number of calculations to do, the fastest way to do this is to string the calculations together. So starting with the mass of aluminum, which is 1 kilogram, this gives us 1.00 times 10 to the 3 grams of aluminum. Converting from mass of aluminum to moles of aluminum, we would divide by the molar mass, which is 26.98 grams per mole. So dividing by this, we see that the grams of aluminum cancel, leaving us with moles of aluminum, which is what we wanted to calculate. To convert from moles of aluminum to moles of ammonium perchlorate, we need the stoichiometric coefficients. So here we would multiply by 3 moles of ammonium perchlorate and divide by 5 moles of aluminum. Once again, the moles of aluminum cancel, leaving us with moles of ammonium perchlorate, which is what we were interested in. To convert from moles of ammonium perchlorate to mass of ammonium perchlorate, we need the molar mass, which is 117.492 grams per mole. And again, we'll see that the moles of ammonium perchlorate cancel, leaving us with mass of ammonium perchlorate in grams. Multiplying this in our calculator, we get 2,612 grams of ammonium perchlorate. Finally, it's important to remember that our final answer should have 3 significant figures because this is the smallest number of significant figures in our data. And rounding, therefore, gives us 2.61 kilograms of ammonium perchlorate. Lastly, we want to check our work to make sure that our answer is reasonable. And you'll notice that the value is in the kilogram range, which is reasonable because we started with a kilogram of aluminum.